Right? So again, I only do this graphically in this chapter, but the formulas of the optimizations behind it are not kind of very difficult. So let's maybe find these assets that we have here in the plots up there. So we have a 10% volatility and a 20% volatility, and the return goes up to 25%. So the first asset that we have is the risk-free asset, and remember risk-free means volatility 0. So that's here, and the expected return of that is the risk-free rate, that's 5%. Then our first asset A has a risk of 10% and a return of 10%. So that's found here. So that's A. And then finally in the upper right corner, we have one asset with 20% volatility and 25% expected return. And that will be our asset B. In the first example, we are mixing a risk-free asset with asset A. In the second example, we're mixing A and B together and then see how the graph looks like. Basically, I want to know, for example, in the case if you look at two risky assets, I want to connect the dots between A and B. What shape do I have to go? Is it like a straight line from A to B? Or maybe is it a weird shape or any other curve? So that's what I call feasible portfolios first, right? So where can we theoretically end up? Right? Are there spots that we cannot go, basically, based on this? Even though they might be very desirable. Right? So ideally, I want to have an asset with 0 risk and a very high return. But in that upper left corner, there is no asset, right? And I can kind of choose my portfolios as I like. I will not end up in the upper left corner, right? That's possible. So, and after that, I'm going to introduce the assumptions of the portfolio theory by Markowitz and kind of what is then the consequence for optimal decisions. So I'm going to denote the weight of our risky asset A here with just W. I'll leave out the numbers to make the formulas a little bit shorter. But here this will be our weight of asset A. And then conversely, the risk weight of the riskier asset must be 1 minus W. And we allow those weights also to be larger than 100% and negative. And now we can apply the formulas that we've just developed so far. So the portfolio return is W times the expected return of A, which is mu, plus 1 minus W, the expected return of the risk-free asset, which is just the risk-free rate. And then you can multiply this through to get the following expression: the risk-free rate plus W times the difference between mu and R. This here is expected return of A. Remember, the expected return is what we want to put on the y-axis of our plot. One thing that you see here is that for our plot, that poses a little bit of a difficulty because the volatility is not in there. Right? So we have an expression depending on the portfolio weight, but on the x-axis in the previous plot here, we didn't use the portfolio weight, right? So I have a function now depending on the portfolio weight, but I don't know what its risk is. So for the risk formula, we have to use the portfolio volatility that will be put on the x-axis. And there is also a formula that only depends on the w's. So the sigma here will be the variance of A. So the portfolio risk is the portfolio weight of A times the variance of A plus 1 minus W, the variance of B of the risk-free asset, which is 0. And of course, we could have a covariance term there, a correlation coefficient, but the correlation coefficient between something that's risk-free and any risky asset is always 0. Consider the risk-free asset as a constant, something that you will always get. And if you have a constant and something that's moving, the correlation between those two things will be zero. Right? The risk-free asset or the risk-free return is not changing depending on what the market is doing. Right? So the covariance or the correlation between these two is zero. So the correlation of anything to the risk-free asset is zero. Again, if I want to shorten this a little bit, this part here becomes zero. I can take the square root of this, and then I will get to the absolute value of the portfolio weight times the volatility of the asset A. This bar here means absolute value. And the absolute value here is important because if we have a negative portfolio weight and we forget the absolute value, then the volatility would be negative. However, that's a range of values that doesn't make sense. Volatilities always have to be positive or the minimum is zero, but they can never be negative. So we have two formulas, both depend on the portfolio weight, and I want to kind of put them on the x and the y axis. So there are two approaches now to solve this. So first of all, in Excel, you could do a table of values. So you choose a certain range of values for the portfolio weight, say minus 100% up to 200%. That's your first column. And then you compute those two things, the return and the risk, for every portfolio given a certain portfolio weight. And then we second in the third column, and then you just create a plot, the XY plot, with this on the x-axis and this on the y-axis. You would have to create a column with three values, and you only plot two of them. The other thing would be you solve one equation for the other, right? So the W, you can solve for the W and plug in the other equation, right? And then you would get a formula linking mu to sigma, and then you can put this in the plot. I spare you the formulas because they look a little bit wild, and there is nothing that we can learn from this economically, but technically it's of course feasible to do. Any questions regarding the setting? Then let's see how this looks like, and that's shown on the next page. So all possible feasible portfolios that we can get are on this line here. And we can find, first of all, let's identify where our assets are. So we have our risk-free asset down here. So that's our risk-free asset. And then here we have our risky asset A. And it appears that if you have one risk-free asset, one risky asset, all those portfolio combinations will be straight lines. And this is a general result here. All the portfolio combinations with one risk-free asset are linear functions. But we have to look a little bit of kind of what happens here, because this negative value here, that looks weird. We have to explain what happens, and why there's kind of this little kink here. So behind every dot in this graph here, there is a different portfolio weight. So maybe it's worth thinking about what are the portfolio weights that are behind this to create this. So I think the most obvious part will be the part here between A and B, the risk-free asset and A. So the blue line here, these are all combinations where portfolio weights of both assets are positive and smaller than 100%. So for example, asset A here, if you are there, that will be a W of 100%. Right? And this dot here in the middle, that will be a W of 50%. So if you are on the blue line, you are in a range of values where the W for asset A is between 0 and 100%. Right? So you have a certain amount of money, you spend part of your money on the asset A, and the other one you put on your bank account. That's kind of what I call the usual situation.